So let's talk about the product rule and why it makes sense. It's a lovely way to take the derivative of a product of functions. We're going to first listen to Mr. Haas give kind of a nice visual, intuitive explanation for why it works. And then we're going to look at a proof of the product rule, a more formal proof. After that, we'll look also at a formal proof of the quotient rule. Are you ready? Here's Mr. Haas.
Imagine that A and B represent the sides of a rectangle. So A times B, of course, would be the area of this rectangle. Now imagine I'm stretching the rectangle in the horizontal direction, so A is changing, the length of A is changing, and I'm stretching it in the vertical direction here, so B is changing. Right? And a derivative is really a description of how something is changing, right? It's the instantaneous rate of change or the slope of something. So my derivative represents the change in the area of this rectangle. So let's think about how the area of this rectangle must be changing. So remember, my rectangle is being stretched in the horizontal direction. So I'm representing that with this little sliver right here. This little orange sliver represents the change in area as I stretch it in the horizontal direction. And I'm calling this little slice the change in A, right? A derivative is really just how something is changing. So this is how A is changing times B, right? That's the area of this little orange rectangle. And the rectangle at the bottom represents how my area is changing when I stretch it in the vertical direction. Now this little amount right here is just the change in B times A, length A. So how could I describe the change in my rectangle's area? Well, clearly it's just the sum of these two little orange slices. Well, this is just A prime B plus A B prime. Hey, that's the product rule. So
Mr. Haas is the best. Okay, so now here is a more formal proof using the limit definition of the derivative where, where we started with all this derivative stuff. Remember, the limit definition of the derivative makes it really obvious that a derivative is a slope between 2 points that are infinitely close to each other, and therefore a slope at a point or an instantaneous rate of change. Pause the video and try to go step by step to try to figure out what is going on here. All right, how did you get on? So in this first step, I am writing this product um, as a derivative, right? Finding the slope between 2 points, h apart. So f of x plus h, g of x plus h, minus f of x, g of x over h. Okay, just good old-fashioned limit definition of the derivative. This step is pretty sneaky. Ah, it looks like I added 0 to this expression. Is that legal to add 0? It sure is, and mathematicians do this all the time, adding 0, multiplying by 1. So look, this first part here obviously came from here. This last part was here. If you look at those two terms, they are identical except one is positive and one is negative. I just added 0. Why did I do that? So I could split this up into 2 fractions. I think if you look at that, that's legal. Now, if I look at this numerator, they both have a common term of g of x plus h, so I factored that out. Here, both of these numerators have a common term of f of x, so I factored that out. And now I'm at this line. So here I have the limit, blah, 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 times g of x plus h plus. Now, some of you might wonder, well, why is the f of x in front of the limit? Well, I'm allowed to put it there because there's no h there. So the limit as h approaches 0 has no impact on this because there's no h, right? So that's why I was allowed to write it in front. I didn't have to write it in front, but I did. Now, here I am. Hey, this piece right here, that's just the derivative, f prime. As h is approaching 0, that's just g of x. This is f of x. What's this right here? Oh, that's just the limit definition of the derivative, g prime of x. And there is your product rule. How cool is that? Ready to try the quotient rule? All right, for this quotient rule, I'm actually going to make you do it, but I'll walk you through step by step. So let's let q of x be equal to f of x divided by g of x. So just walk through step by step and see if you can arrive at the quotient rule. Pause the video and give it a try. All right, how did it go? Let's see. So here I am. I did the cross multiplying. Product of the means is a product of the extremes. I just put q of x over 1. Then I used the product rule to take the derivative. I replaced q of x with f of x divided by g of x. If you go back here, obviously that was just how q of x was defined. Then I solved for q prime of x. And this is kind of the tricky algebra. I now have a fraction in a fraction, so let's get rid of that fraction. One handy way to get rid of any denominator is just to multiply by the denominator. So I multiplied the top by g of x and the bottom of this fraction by g of x. Hey, I'm multiplying by 1. And here we are. If you look at this, you'll recognize this as our familiar quotient rule. Pretty cool.